this example, we have two wires. It says that they're pinned to the ground, so these two stay in place. They're separated by a distance r. Let's draw this on the picture. The two wires carry current I in the same direction. So I1 equals current I2 equals current I, and both of those guys are into the page. A third wire with mass M is carefully placed above the midpoint of the two wires. Okay, so right above the middle, that makes this a right angle, and is seen to hover such that the three wires make an equilateral triangle. What is the current in the third wire? So first we have to get the direction of the current. We know that wires that have currents in the same direction attract each other. Wires that have currents in opposite directions repel each other. So this one must have a current coming out of the page. We'll see that we're right as we go through and we figure out what our forces are. But we know right off the bat that in order to get this to float, it has to offset gravity, so there has to be a magnetic force that points up. To get our magnetic force pointing up means it's repelling, which means that the current has to be opposite. So the direction of the current is out of the page. So where we're going to go with this is, let's write that the sum of our forces in the y direction equals 0, because that's what's going to get this to float. What forces do we have? Well, it says that the wire has mass m. That tells us that gravity is going to be part of the story. And there are also going to be magnetic forces due to wires 1 and 2. So our gravity force, Fg, that's going to be mg. Magnetic force is going to be the magnetic force due to wire 1 and the magnetic force due to wire 2. Okay, so we want to write down expressions for each of these forces. When we sum them all up, we know that the sum of those forces will be 0. As we work through that, we should be able to get an expression for the current in the third wire, I3. So there's the plan. Let's think about our magnetic forces. We know that magnetic force F is IL cross B. If we're going to get that force, we're also going to need that magnetic field. Okay, so the first thing we'd like to do is let's figure out what's the direction of the magnetic field due to wire 1 at wire 3, and what's the direction of the magnetic field due to wire 2 at wire 3. I'm going to spill onto a separate page for that one so that this diagram doesn't get too messy. Okay, now, so wire 1 is right here. The current is going into the page. What we know about current carrying wires is the magnetic fields that they make big circles around the wire. Let's draw that circle. What's the orientation of the circle? We use our right-hand rule here, where our thumb goes in the direction of current, so into the page, and our fingers show the orientation of that circle. So the magnetic field is coming around this way. The magnetic field at this point, where wire 3 sits, is going to be a tangent to that circle. So it's either going to point up this way or down this way. How do we pick between up or down? Well, it has to go with this. And right here, according to this one, we see that it goes down. So there's our magnetic field, B1. To find the direction of our magnetic force, we can use our right-hand rule. We know that FB equals IL cross B. For this one in particular, FB is going to be I3 times the length times B1. So we point our thumb in the direction of L out of the page, our finger in the direction of B1. It's getting a little painful, so I'm just going to turn my paper around. So current is this way, magnetic field is this way, our magnetic force comes this way, perpendicular to B1. So there's our force F due to B1. Okay. So that takes care of the direction of the magnetic force due to wire 1. Let's also get the direction of the magnetic force due to wire 2. Wire 2 is on the lower right-hand side, so there's wire 2. The magnetic field it makes are also big circles around the wire. To get the orientation of those circles, we use our right-hand rule. Thumb goes with the current, and we see that our fingers are curling around up this way. Our magnetic field is a tangent to the circle, so it goes this way. It's either down or up. And we see that our fingers point up, so it must be up. So there's our magnetic field B2. Current 3 comes out of the page, so when we do ILB, so for this one, FB for wire 2, and this guy was for wire 1, is equal to I3L crossed with B2. So thumb goes with the current, finger goes with B2, extended middle finger shows the force. There's your force, F magnetic, due to wire 2. Okay, now we've got those force directions. We see that they're really just extensions along the radius of the circle. Let's go back and draw those on the previous slide so that we get a complete free body diagram. So here on our free body diagram, let's put in the forces that we have. The force due to wire 1 pointed up and right, FB1. Force due to wire 2 pointed up and left, FB2. And the other force we have is the force due to gravity, so that points down, FG. Okay, so there's our free body diagram. Let's write in the sum of our forces in the y direction. Sum of the forces in the y are FB1y plus FB2y minus because it points down, FG equals 0. So let's figure out each of our things that we're going to fill in. What's FB1y and FB2y? That means we want to find the y components of our forces. There's the x component of force 1. There's the y. FB1y, FB1x, FB2x, and FB2y. If we're going to find x and y components, then we need to find some angles. We know we need to use sine or cosine. That angle is theta, this angle is theta. We know that it's an equilateral triangle. That tells us that theta equals 60 degrees. And each side has the same length. So FB1y equals FB1 times sine theta. I'll just write theta for now so I don't have to write 60 over and over. FB1 is the force on wire 3 because of wire 1. So FB1, I'm going to fill that out down here, is I3 times L times B1, but B1, oh, wire 3. B1, oh my, I'm just making a mess of that. I3 times L, B1 is mu naught times I1 over 2 pi r. It's an equilateral triangle, so this distance is also r. There's our FB1. So to get the y component, we take this and we multiply by sine of 60. What we know about sine of 60 is that it's root 3 over 2. Okay, you can put that as a number if you wish, or you could even just leave it as sine 60. I'll fill in root 3 over 2. So let's put these guys together. It gives us mu naught times, oh, and our I1, we said I1 was just equal to I. So we've got mu naught L I 3 over 2 pi r. So we've got mu naught times L times I3 over 2 pi r times root 3 over 2. FB2y is going to be exactly the same thing. The two wires have the same current, they're at the same distance, they both point up, so it's going to be the same. And if you wish, you can go through this entire process, but you'll see that you get the same result. So that's our magnetic forces. Our force due to gravity, of course, is mass times gravity. It says the mass is a capital M. Now our sheet is filling up here, so let's spill down to another sheet. So let's fill in the expressions for each of our forces in our Newton's second law. So we've got mu naught times L times I3 over 2 pi r times root 3 over 2 plus same thing again, mu naught L I3 2 pi r root 3 over 2 minus m times g equals 0. So now what we're doing, now our job is, let's just solve for I. So let's take I3 is what we're trying to find. We've got I3 outside of mu naught L times I times root 3 over 2 pi r. If you're wondering where did this 2 go, got 2 of these terms, so it would be 2 times this one. The 2 on the top would cancel with the 2 on the bottom, so that's where that 2 went. Minus mg equals 0. So then I3 is equal to mg times 2 pi r divided by mu naught times L times I times root 3. And the direction of that current is out of page. Okay, that was kind of a complicated example which had a lot of vector stuff in it, but the idea hopefully is a little bit simple. The magnetic force had to balance the force due to gravity.